Hello everyone. So today we're going to start talk about 9.3 surface integral. So what is a surface integral? So in chapter 8.1 we have learned to integrate a vector field F along a path. It is called a line integral. So what we're going to try to do now is to try to apply this concept not along a path, but rather over a surface instead. So in 9.3, we will try to apply the same idea to define an integral of a vector field F over a surface. It is called a surface integral. So the question is, how do we do that? But before we actually get to talk about how to apply this concept to integrate a vector field over a surface, let's talk about a surface first. So in chapter 4, we learned the following. A surface, and we'll be focusing on in R3. In R3, can be defined parametrically as a function g, then back from R2 to R3. We will only focus on surfaces in R3 because of the limitation of what we have to work with. The concept might apply to higher dimensional surfaces, but we will focus just mainly on R3 for our class. So therefore imply that our surface would be defined by g of uv, which is equal to g1 of uv, g2 of uv, and g3 of uv. And you can think of g1, g2, and g3 as x, y, z. And over some regions in the uv plane. That would be the domain. So let's try to understand this process a little bit. So the general idea is the following. Imagine I have a UV plane. So this is my domain. And if I take this domain and plug it through the function g, we'll actually get a surface that's in R3. Now, for now, I'm going to go and try to draw some kind of regions in UV. So let's say we have some kind of regions in UV right here. So that would be my domain. So maybe I'll write that as the UV plane. And then this is the XYZ space. Then this, after I plug into function g, will form some kind of surface. So in this case, this surface will actually be finite because our domain is finite. And we are assuming that this form a nice surface that doesn't go off to infinity, doesn't have any break, often referred to as a smooth surface. Okay? Now, here's something that you probably remember learning. So let's see if you remember. We talked about this back in chapter 4. Okay, 4.4 to be exact. Imagine I pick a point somewhere on in the domain. It doesn't matter where I pick it. So I'm going to just go and pick it right here. Here's the point u sub 0, v sub 0. Okay, I'm picking quadrant 2, but it doesn't really matter where it is. So that point will corresponding to a point right here, which is g of u sub 0, v sub 0. And I can say this is equal to maybe x sub 0, y sub 0, z sub 0. So this point is corresponding to that point. Now, let's see if you remember. What if I now draw a horizontal line and a vertical line through this point? So notice that the horizontal line would actually be v equal to v sub 0, and the vertical line would actually be u equal to u sub 0. The question is, what happened to these two lines? Well, these two lines actually have a name, and hopefully you remember. They're called coordinate curve on the surface. They basically meaning that they're curve formed by when you move the point along a direction that parallel to the coordinate axis, one of the coordinate axes. So in here, the red line will form some kind of curve that go like this. Okay, while the blue line might form a different curve that go kind of front and back, or maybe in a different way, we don't know. So this one is basically called the coordinate curve of u, because v is fixed, so only u is changing, while this one is called the coordinate curve of v, because u is fixed, so v is the only one that's changing. And here comes the important part. If I now look at these two curves, I can actually form the velocity vector of these two curves. And they are actually given by partial derivative. So therefore, we can imply that we can figure out that the tangent to this curve on this point right here, this is actually dg over du, dg over du at x u sub 0, v sub 0. And it might have a second derivative, dg over dv at u sub 0, v sub 0. So those are what we call the tangent vector at the point g of u sub 0, v sub 0. So therefore, this picture shows that we have dg over du at u sub 0, v sub 0, and dg over dv at u sub 0, v sub 0. And they are basically called the standard tangent vector for the surface at the point u sub 0, v sub 0. And some of you might already thinking like, oh, are we going to talk about the tangent plane? Yes, we could use these two tangent vectors, standard tangent vector, to form the tangent plane at the point g of u sub 0, v sub 0. And as a matter of fact, if you look back in all the tangent formula you have written during the differential calculus part of this course, you probably recognize one of them. Actually uses these two partial derivatives. But that's not what I want to talk about. I'm actually going to introduce something more important than these two tangent vectors. So what could be more important than the two tangent vectors at any given point? Because they literally show you like which way you're moving on the surface. Well, it would be this. If I know these two tangent vectors, I can now define what we call the normal vector. The normal vector for the function g of uv at the point u sub 0, v sub 0 is given by the following. By taking the cross product of these two standard tangent vector. And that is basically form what we call the normal vector. Now, I know some of you are probably thinking like, well, why don't we just call it perpendicular vector? Well, there's a reason for that. Perpendicular vectors tend to be referred to a perpendicular vector of a flat plane, which means that the perpendicular vectors tend to be something that's be the same for the entire surface, where the surface is completely flat like a plane. But since we have a surface that changes, we often refer to it as a normal vector instead. So it's slightly different, but in essence, they are literally the same thing. So that's how we calculate normal vector, is by taking the cross product of the standard tangent vector at the point. Now that becomes relevant later on. So in general, the normal vector for g of uv at any point is given by just taking dg over du cross product with dg over dv. And then that will give you a formula that you can then use to evaluate the normal vector by plugging v sub 0, u sub 0, v sub 0. So that would be important later on, so make sure you keep that in mind. So now that we know the normal vector, which is right here, the next thing I want to talk about is what are some of the uses for the normal vector. Well, as a matter of fact, one of the ways to use the normal vector is to actually calculate the area of the surface. Now, I know we have learned how to calculate area already, but this is different. The reason why this is different because the following. We actually haven't learned any way to calculate area of a surface in R3 yet. Yes, we have learned how to calculate volume in R3 through a double Riemann integral. The only way that we know how to calculate surface area in R3 is through a surface of revolution. But we're not doing that here. So, as a matter of fact, in all the math that we've done, we have talked about how to calculate area, but just not for area in R3. So, a quick recap. How many different formulas you know to calculate something, an area in R3? Calculate just area in general. So, next thing we want to talk about is area of a surface in R3. So, in BC calculus, you have learned to find area under the curve. Well, actually, maybe I should say area between a curve y equal to f of x and the x-axis over an interval from a to b by using this integral. So I'm going to say a equal to integral from a to b f of x dx. And of course, when I say area, loosely defined, I mean, technically speaking, it's a net sign area, but I'm going to assume that the f of x is always positive in this case. Okay? And in chapter 7, we also learn how to calculate area. You have learned to find area of a region's, let's say, R in, actually, you know what, let's not use R, let's say B. I guess R is okay. In R2 with a double Riemann integral. A of R is equal to double integral over R dA. So that allows you to find the area in R2. So now what we're going to try to do is now, what if we have a surface in R3? How do we calculate the area of this? So in chapter 9 right now, we will learn how to calculate the area of a surface in R3. So how do we do that? So here's the general idea. Let's say we're given a parameterization of a surface in R3 over a domain D in the UV plane. Okay, so therefore imply that, let's say we have the UV plane and we have some region. You know what, actually I'm going to write it this way. I'm just going, for simplicity reason, I'm going to just put it in the first quadrant. So here's D. So that's our domain. And it will transform into some kind of surface in the XYZ space. So once again, I'm going to draw some kind of surface. Okay, so here's the function g of uv, and then this would give us the g of uv equal to, let's go over here, g of uv equal to xyz. So now the question is, if I want to find the surface over here, how do we calculate that? So I'm going to go and call this surface S. Okay, so we're going to go and call, let's say, the image of g of uv is the surface S. So the quick big question is how to calculate the surface area of S. So the way to do that is to, obviously, just like how we deal with a lot of these things, Riemann sum, integration. So here's how it works. So imagine I start with a point somewhere over here. I'm going to call it u sub, I guess I can call it u v for now. Okay, and that will corresponding to a point over here, which is g of uv. You know what? I'm going to give it a subscript. I'm going to say u sub t, v sub t. Actually, you know what? I don't like t because that's like a perimeter. So how about k? K sounds good. Let's do k. Okay. So now, remember, I could now define these two curves, which would define two coordinate curve at this point. But I'm actually not interested in the coordinate curve, but just simply interested in the tangent vector. So therefore, I can say that it would form probably a two different tangent vectors. One of them go this way, which is dg over du at u sub k v sub k, and maybe a second tangent vector. Let's go this way, dg over dv at u sub k v sub k. So those are two directions that will be going at a straight line from this one point. If I were to move this point either to the left or to the right in the u direction, or move up and down in the v direction. So now imagine the following. Imagine that, let's see, I'm run out of color. I'm going to use red. It's okay. Imagine that I do the following. I simply move this point slightly this way and slightly this way to form a rectangle. Well, not necessarily form a rectangle, but just simply move it. Oops. I guess I can just redraw. Slightly moving this either direction. So I'm going to go and call this slightly movement this side delta u sub k, and slightly move up as delta v sub k. What they would do is they would, technically speaking, move this point in the XYZ space along the two different directions. Basically achieve the fact that they would move it slightly over and slightly over in the direction, and the way to calculate this direction would basically be just multiply this direction vector, the tangent vector, with the change that I made in u and v. So therefore we form this somewhat zoom in picture. So here's the point g of u sub k, v sub k. And let's say here's the direction. Oops, actually I'm using blue. Blue is this direction, which is dg over du as u sub k, v sub k. And this is the direction dg over dv at u sub k, v sub k. So now if I simply move this one point by delta u sub k and delta v sub k, then I would basically allow this point to move along these two directions slightly. So how far does it move would actually be equal to this. This would actually equal to dg over dv at u sub k, v sub k, multiplied by delta v sub k. Similarly, this one on the bottom will be dg over du at u sub k, v sub k, multiplied by delta u sub k. So the delta u sub k and delta v sub k simply scale the direction vector to a different length. Now, why is it important? Well, the reason why it's important because the following. Now that I have these two direction vector, I can now actually form a parallelogram. Ooh. All right, let's see if I can do this. Oops. Okay, got it. Let's see if I can do this. Oops. What happened? All right, here we go. Nope, that's not what I want. I'm going to try to move this out of the way. Let's see if I can do this. Oh, maybe this would help. Nope. That's probably do it. I'm going to move it down here. Okay, there you go. Much better. So now with these two direction vector, I can now actually form a parallelogram. And I can actually calculate the area of this parallelogram by using cross products. You probably remember learning that back in chapter 1. The area, in this case I'm going to call A sub k, would actually equal to the length of the cross product of these two vectors. Oops, I think I would use u first. Technically it doesn't matter, but I like to use, just put it in the right order. Since delta u sub k and delta v sub k are meant to be a constant, I will now pull both of them out of the cross product, and now I have this. And that gives me the area of one of these parallelogram. So imagine I just start putting in a lot of different points, and then each one draw myself a little parallelogram like this. And obviously I'm trying to do it in such a way that they don't overlap each other. I would be able to approximate this surface area by using a whole bunch of these area parallelogram. So essentially taking this area and kind of cut it into a whole bunch of smaller parallelogram and a positive area. So I can then say the total area will be approximately equal to the summation from 1 to n of a sub n, which is basically summation k from 1 to n, the length of dg over du at u sub k v sub k, cross dg over dv at u sub k v sub k, multiplied by delta u sub k, delta v sub k. And if that gives me an approximation of the total area, I can then say the total area should equal to the limit as n approaches infinity of this summation. And as you already know, this is a Riemann sum, and therefore allow me to transform this into an integral. And that integral, well, let me write out the Riemann sum first. So here's the Riemann sum. So this is once again a Riemann sum. And as we all know, a Riemann sum will transform into an integral. So this integral will calculate what we call the surface area of S, which is this surface right here. And that is given by this symbol, sigma of S. And that's equal to a double integral over the domain D of the length of dg over du of uv, cross product dg over dv of uv, du dv. That is called a surface area of the regions S. Now, I know I don't have much time, so I do want to talk about two more things. In this expression right here, this part right here, du dv, is called a surface integral, a surface differential. Actually, I think it's called a surface area differential. And the notation for that is this. This thing is sometimes called d sigma. And so therefore you can think of the surface area of S is actually equal to double integral d of d sigma. A kind of condensed version of calculating the surface area. Now, of course, one last formula, and that's it for today. And then tomorrow we can, next video, we can then talk about doing example. What if we try to calculate the mass of this surface, assuming that this surface has some kind of density? Then I can actually calculate this mass in using this integral. with density function. And it would be given by this double integral over d of the density function of g of uv multiplied by basically the surface area differential, which is this. Alright, unfortunately that's all the time I got for today's video, so I'm going to stop right here and we'll continue some more on our next video. Alright, talk to you guys then. Bye bye.